Yeah, let's start. So we have again, so very important lecture today. It's maybe arguably one of the most exciting lectures in terms of like low-level systems functionality. So it's about the context switch, essentially how we switch from one context to another, one process to another. And we first will quickly finish what we were talking about last time. So remember and then move on to the context switch. And this material here will be important later today. So remember, like a quick reminder, last time we were talking about exec, right? Exec essentially replaces the address space of a process, right? And so that's what we learned last time. And we said, okay, we got it. So like, let me just scroll back here. So we say exec is a big function, but what it really does is that it creates a new page table for the new process. I mean, it's the same process, right? So, but it creates a new address space. It allocates all these pages for the new like data and text sections for like, for example, if you invoke bin_ls, so bin_ls will be sitting here. We learned that we allocate a stack, and below the stack we allocate a guard page. And what we learned two functions: one which allocates the address space, right, those pages, and a second one loads this address space from disk, right? So essentially scrolls through like you open an elf header and then load section by section into these pages, right? And we spent some time discussing how we actually can access pages or memory of this new address space, because you cannot use the virtual addresses directly, but you have to essentially, because the CR3 is still loaded with the old address space, and then we like do this trick where we know that all the physical memory is mapped. So if you need to access, for example, this page, instead of like really using the virtual address 0, and imagine this page is mapped somewhere here, we really do this, walk the page table, figure out the physical address of this page PA, and then we do P2V, like a shift was a 2 GB, and really using this virtual address, right? That's a quick reminder what was happening last time, right? And then we said, okay, look, conceptually, despite like being a little bit tricky to do all of it, so conceptually it's reasonably simple. Like create a new address space. And when we wanted to start running, we said, okay, look, we allocate the stack, allocate arguments on the stack, right? So that's what we talked about. And at the very end, like essentially switch the page tables. This is the very end of the exec function. So, and essentially return. At this point, we're running on the new address space, and at some point we're gonna like exit back into the same process. And what we've done here is that we essentially created the new address space, right? And that's all nice. So we understood all of it, but what we wanted to talk about at the very end is how we really create the very first process, right? Remember this trick. And so I started to say, okay, look, we got it. So we know if we have a process, we can either fork and create a new one. And this fork, there's a couple of questions about fork on the quiz, right? Which is due on Thursday. And we can reload, after we fork, we can reload the address space with exec. So we can actually have something new running. So a combination of fork and exec allows us to create a new process for real. But the question is like how we created the very first process in the system. And so what I was talking about, I said, okay, before finishing the main function, we enter the function which is called userinit, and we say, okay, well, this function will really create the very first process in the system, right? And conceptually, again, we said it's very, very simple. What we're gonna do is that we allocate the data structure which represents the new process, right? So, and there is a function in x_6 which says, okay, allocate a process. As I said, x_6 doesn't really implement a general memory allocator. Instead, what happens is that x_6 has array of possible processes, right? So, and initially this array is all free, and this alloc proc essentially is scans through this array, kind of like a bitmap saying, okay, if these two are allocated already, I will pick a third one, right? And this entry in this array will be this proc data structure, which essentially represents all the information which you need to know about the process, right? So, like for example, the kernel stack, page directory, page table, and stuff like that, right? Okay, cool. So we understand this, but really, what is the machinery? If I ask you a question, so how will you really create a new process? What's the easiest way? And you can say like, yeah, I will load multiple ways to do that. Okay, so any suggestions? And like, to be honest, your next homework will be to create a very first process in your wonderful Hello World operating system, which we're building right now in a series of homeworks. But how can we do this? What needs to be done?
Seems we can copy everything from the main process, but we need to have new user space, address space.
Well, okay. We obviously, like when we say, okay, we're going to create a new process, we allocate an address space, right? With this address space, since we said, okay, in our operating system, the kernel part of the address space is always mapped. So we will map the kernel part of the address space. We have this function, right? So the question is like, how will we create this user part? And yeah, go ahead.
Since the kernel space is initialized, should we grab from the free memory page part of the kernel, or is that not available?
Well, so when we created a page table, right, we mapped this part, right? Your high-level idea is to have some executable user code running here, right? Similar to how we did for exec. Why not? But how? Like, what mechanically, what would you suggest to do? I mean, really, yes, you can implement an extra function which loads something from disk, right? That should be okay, right? But this, you can say, I will build a function, something like create first proc, right? But this function in the end will be very similar to exec, right? Because it will have to do same steps. It will have to take the name of the process on disk, create the address space, load the stuff from disk, create the stack, do all of these steps, right? So you will end up with two very similar functions. One, create first process, another is exec, right? And of course, it will be harder to maintain if you have a bug in one of them, you have to fix another one as well, because they're almost identical, right? So what x86 does is they say, okay, sure, we gonna reuse exec as much as possible. And instead of building this function, we will create a very minimal trampoline code, which we load into this one page. We're gonna break the invariants here. We collocate the stack and data on a single page. Well, it's not necessary, but you can use a couple of pages, but really one is enough. And this tiny assembly code will simply invoke an exec system call, because like then you can just simply replace this address space with whatever you want, but using exec and already existing functionality, right? Does it make sense? Okay, so and this is what x86 is doing. So they said, okay, we allocate a minimal page table, right? And we will use this binary trampoline code. So essentially, it's an assembly sequence which x86 essentially bundles, or like it. If you make a picture, so this init sequence is included as part of the kernel. So this is init. this init, the very first process, which is marked with this two symbols, the start and the size, right? And we like, I'll explain how it's done in a homework assignment, but really it essentially, those two labels show you where this assembly code is located inside the kernel, right? Inside the data section of the kernel, right? And so what they use this function init UVM, so it's essentially it's very similar to how we did it in the past, loading something from disk, but really what we're doing here is simply just copying this assembly sequence into the address space. And so specifically internally, what this function is doing, it says, okay, like I will allocate a page of memory, right? And actually they do a check here that the size of the thing which you're trying to initialize is actually less than a page, right? It will immediately panic if you try to pass the size which is greater than a page. This function is so specialized that it will simply allocate one page. So no loops, nothing, right? Set it to 0, map this page into the page directory which you pass here, right? At the address 0 with user accessible, writable, and then you simply copy this init code into this page, right? And if you look at it, so what does this init code contain? The init code is literally a very minimal assembly trampoline, which ends invoking a system call. And it's exact system call. It pushes arguments on a stack. The stack is collocated within the same page. So here, where is our stack here, actually? I probably lied to you. The stack is actually allocated as part of this stack is allocated outside by the kernel, right? So this guy, so there will be an ESP set up by the kernel before exiting into this process. And but like all the arguments are essentially here within this assembly sequence, right? And so when you created this stack, you're essentially ready to go. So this alloc proc essentially, I apologize. So alloc proc for each new process, alloc proc actually allocates a kernel stack itself. It creates a trap frame. Remember that if you want to exit into the process, you need to essentially have this trap frame sequence on the stack, on the kernel stack, because when you will gonna be returning using IRET eventually, you will be restoring those registers, right? So all of it is initialized with this alloc proc function. And specifically what happens here is they say, okay, so like we will initialize the code segment, data segment, other segments. So this is the segments are initialized with user privileges, and the stack, instead of allocating a page for the stack, they say, okay, hold on. This is the trick. So they say the user stack pointer will be just pointing to the very top of this page, right? So effectively, because again, the process itself will only have one page, and essentially the stack will be at the very top of this page, right? And the user instruction pointer will be 0. So it's essentially beginning of this assembly code, right? And if you do everything correctly, all of these registers are initialized. This instruction pointer we just set to 0. The stack pointer is set to 4096, the top of the page. Essentially, when you start returning from this on this kernel stack and do an IRAT, you will start running the first assembly instruction in the init code. And that's essentially the trick which x86 is doing, right? After that, since it creates a new process, it says, okay, I will give it a name. It will be called init code. Remember, the process data structure has a name field. The current directory will be root of the file system. And again, it's a pointer to an inode. They use a name function to make sure that they have a matching inode. And then they set the state of this process is runnable, which means that at some point in the future, the operating system will switch into that process and will start running it, right? And essentially today we're going to talk about how we will eventually switch into that process, right? Let me stop here. Any questions about it, how it works?
Before we do the like the init code in the first page, what's the user space originally is used? I mean, before.
No, hold on. Like, remember how we, let me scroll here for you for the slide. So we are inside the main function. Remember, it's very similar to how we booted into C in your homework, right? So we booted into main in xv6. xv6 did all of this initialization, right? And like towards the end, invoke this function user init. The user init itself says, okay, I'm gonna create a new process with this allproc function. This allproc function internally, right? What it does, it says, okay, let me just show it for a sec. Which slide is that? Can't see. Allproc internally says, okay, I will allocate. I wanted to show it essentially somewhere before that, it allocated the address space. So it allocated the kernel part of the address space. So if I make a drawing for this, you have a process data structure proc. It will have a pointer to the page table. This page table is empty at the bottom 2 GB, right? Because it's a new process and we don't yet know what will be running here. But it has a kernel part of the address space. All processes in xv6 and all address spaces have the same kernel part, right? So it's essentially the kernel sits here, and then all available physical memory sits here, right? Up until fistop, right? Agree? So, but this part is completely empty, right? And what we're doing here is that say, okay, look, we will allocate simply one page here. Then we copy here this init code. Right? Since there is also a pointer to the kernel stack, case stack, which each process has to process interrupts, right? On this kernel stack, we will create a correct instruction pointer, EAP, which will point to 0, right? Because this is where we want to start executing this process at address 0, right? And the ESP pointer will be pointing to the very top of this page, right? And it will be the stack for this process. This process doesn't need a lot of stack. We only want to put the arguments there and just go with it, right? Because what it will do immediately, it will invoke the kernel with the exec system call, and exec will have an argument which will replace this address space. Like exactly how we discussed, like any other exec will work, right? And that will give you a new running process in the system, right? Or like not a new one, but the same, but with a new address space, right? So is that this idea clear?
So before we allocate the first part of this address space, we have the main function, right? So how about the user space of the main function?
Yeah, okay, good question. So if I ask you a question, do we have any user part? If we like, let me use a different color here. So if we're running inside main, who remembers what address space we have for main? What page table? What does it contain?
Yeah, just the kernel part.
Correct. So it only has this part. So it only has the kernel part. And we created it. Remember, we did when we were talking about kernel memory allocator, we said, okay, this is the page table which we create for the kernel. It will never have any user part. It's empty. Because the idea is that the main will never exit into the user addresses. And main currently running on this page table I will make it blue here, right? So in this blue page table maps only this top part of the aerospace, right? And nothing else, no user part, right? Is it clear? Okay. Any other questions?
So you go to the exact set up your initial code, and then you go to exact immediate fix the code.
Correct. And then you will get running something, and I will show you what is that you're running. But it's kind of a shortcut. It's a little kind of like, you can say it's an ad hoc, but it's at the same time a little elegant. But you can design different boot protocols. Like, and you say, look, I really will have a full-fledged function, this init function, which I was which we talked about, as I was saying, which was called from the end of main, can really create a meaningful first process. So instead of like creating this trampoline, which invokes exec, you may want to load whatever you want, like a real full-fledged process. But then it's a little bit, it duplicates the functionality of exec, right? And x86 said, okay, let's do it this way. Okay, so if we're good on that, the question is like, what is that we're running? So what is this? What are we really execing into, right? So let's take a look. So exec, let me show you here, sorry. Where is this? This init code has this string, and it says, okay, by the way, I will exec into /init. And that's really the address space. This is what we're execing into. And init, this init is the real like binary developed in C, like any other regular program in x86. And if you take a look at the source code of this program, this is what it does. So essentially, this is the init process. It has a main, as everything else, no argument. It enters the infinite loop. What it does, it says, okay, when x86 boots, you can see the string on the screen that we're starting a new shell. So what it forks itself. If the fork doesn't fail, it essentially execs into a shell. And this is what you see on the screen when you boot x86. So you're welcome with this, like you're welcomed with a shell. And it's very much similar to how any other Unix system boots, right? If you exit this shell in x86, since it's an infinite loop, it will try to fork itself again and will create immediately a new shell for you. So x86 doesn't really shut down. So it always will be creating a new shell. So there is no way to essentially shut it down, right? But that makes sense. So that's how this init process is always running. It doesn't exit unless you panic here somewhere saying, okay, look, I ran out of memory. I cannot fork for whatever reason. Can happen. Maybe, the user created so many processes in the system that it exhausted all available resources. And at this point, it will like exit. That's kind of the shutdown path in x86. So you can exploit it if you really want. Okay, so this is how we create a very first process, right? Any questions about it? And this is how we really boot into shell on x86, right? And it's similar in other Unix systems, like with slightly different trickery, but conceptually the same idea. Good? Okay, so we got it. We boot into shell. And at this point, we know a lot of things, right? So we spent many weeks to understand how the operating system boots and it initializes itself, right? So like roughly after the midterm, that's what we were doing. We know what's inside each process, right? So we looked at exec, we know how to create a process, and we know how the very first process is created in the system. But we don't really know how we switch between processes, right? And this is essentially, how do we even switch into this very first process? That's the topic of our subject of our today's lecture. And that's what I was saying, okay, maybe it's one of the most exciting topics or lectures, because if you understand all of what we did in a class, you will be able to build your own operating system. If you understand how to switch between processes, your operating system will not only run one process, but will run anything you want, like multiple processes, a real full-fledged operating system. Okay, so let me switch the slide deck and essentially switch to this new lecture about the context switch. Okay. So first, a bit of recap, right? When do we need to switch between processes? Who can tell me? Say this again, when we have multiple processes running, so P1, P2, and whatever, Pn, and when is it we switch?
Whenever both of them have tasks. If you're watching a video on one process and you're typing back on the other, they're both running, you can switch it to the other.
Almost, but let's take it a little bit like one level down. So again, remember in x6, and let's be concrete because this way we'll understand everything. x6 has an array of processes, right? Like each of this is proc. It's proc data structure. I don't know. Today my handwriting is exceptionally bad for whatever reason. Oh, damn it. What's wrong? Erase everything on a slide. What I wanted to say is that P1, P2, so this is Pn. In x6, we have array of processes, right? In the kernel. Just let's be as concrete as possible. So this is like all the proc data structures which have the page table for this process. Imagine you running inside this process, right? Forget about like you're watching a video. In the end, you know, let's just for a second imagine we're inside x6. We're running something. At what moment we're gonna switch?
Because there are so many processes, but we have only limited CPU. So for
Right. For simplicity, imagine we have one CPU, one physical CPU, one physical instruction point, one physical EAX register, right?
Yeah.
So what do?
And if we need to make a fair for every process, so at least after some execution time, we should switch to another process.
Correct. So this is what I was, and it sounds actually like it very natural. You say, look, I have one CPU. Imagine I have 10 processes. This is 10. Should probably label. You say, I will give them turns. Let's imagine each process will run for like 10 milliseconds, right? A human can hardly notice. So some people can notice those ranges of time, but that's hard, right? And if we like switch between them every 10 milliseconds, like you said before, like maybe this one is playing a video and maybe this is a text editor, right? And if you switch really, really fast, the human cannot even notice, right? In fact, only one process was running at a time, right? At each moment of time. But the switch happens so fast that we as humans don't even notice, right? So, and as you said, okay, so how do we implement this? We say, look, we will configure the timer to send us an interrupt every 10 milliseconds, right? And so essentially we're going to switch on a timer. So, and we already know like all the timer interrupt pass. And so we're just going to talk about what happens when the timer interrupt arrives. There are some other cases when the one process switches to another. So for example, if this text editor says, okay, I'm waiting on a keyboard input, right? So really I need to read a key and it will wait on the user input. So it will go into the kernel and the kernel realizes, okay, there is no keyboard, there's no keyboard input in the kernel. It will switch to another process and we'll just simply wait for the user, right? So it will kind of like waiting on IO. So it's another common reason. But we're going to talk this like no matter what the reason is, really like the context switch is always kind of the same. So the pass is the same. So, and we're going to discuss the one which is triggered by the timer. And it's the most common case, right? Because if you really switch very, very fast, so it feels like we're running one system or like that, it feels that multiple processes are running at the same time to us humans, right? Although in practice, only one of them is always running. So is this idea clear? High level idea, right? Agree? So, okay, let's, yeah, sure. So let's take a look. Let's take a look at the timer interrupt. So again, so nothing super special. We already kind of talked about it. So at some point when after the timer interrupt arrives, we end up in this trap function inside the kernel. And I mean, verbatim, you can probably copy this code into your homework assignment, right? So you say, what is my trap number? It's a timer interrupt, or we'll increment a local variable, just like less interesting, but really this is what we care about. We say at the end of this trap function, if the process was running and the trap number was a timer interrupt, we're going to enter this yield function to essentially yield the CPU and let other process a chance to run, right? But we are inside the timer interrupt right now. So inside the yield function, again, we remember that the process was running. So we remember that it's in a runnable state, meaning that it's ready to run later on. And we'll enter this scat function. And the scat function internally will actually do the switch by invoking a low-level switch function, right? And this switch function will switch from one process to another, right? Agree? And our goal is to actually understand in details what needs to happen inside the switch function today. That's our goal. But at a high level, we got the point. So we are inside the timer. We have to switch. So if I ask you a question, so what do you think needs to happen inside the switch function?
Yeah, actually, before this, I have a question.
Okay.
I see when you do the timer handler, it's supposed to be the CPU to be 0. Why? Why we need to specify the CPU 0? Every CPU to, right?
Correct. So in x86, only the CPU 0 maintains this fixed global variable.
If so, why they need a lock, right? If only one CPU, there's no sharing, right?
Correct. So, okay, we're going to talk about locking, but I think this wake up function has to be, it's essentially allows you to implement a system call, which is something like sleep. Sleep says, okay, please go to sleep for 100 milliseconds or something, or a second. And the process enters the kernel and waits in the kernel for 100 milliseconds. And this wake up function, essentially, like it counts the ticks and it wake up everyone who is waiting. So when you enter the sleep function, you say, my current tick variable is, let's say, 77. Since I'm waiting for 100 milliseconds and the tick is incremented, let's say, every 10 milliseconds, right? So I have to wait for 10 ticks. So I will be woken up when it reaches 87, right? And there is a specific data structure, and this wake up essentially wakes up everyone who's waiting on 87.
So 2 questions. One, is this just called whenever a process is initialized?
Good question. So what do you think? So, okay, let me rephrase the question. So the question is, when is this trap function running, right? So what's the answer? Who knows the answer? Related to the homework assignment again. Remember what I asked you to do in the homework. I don't know if you started, but I asked you to print a dot. And the correct answer to the homework assignment, we will see a bunch of those dots being printed, which means intuitively that the timer interrupt is running all the time, right? And this is how we configure the timer. So this initialization code, which I kind of like glance over because there are many details, just sets up the period of a timer. And you can set it differently, but let's say 10 milliseconds is a reasonable value in real operating systems, right? So which means that the timer interrupt will be arriving the moment you re-enable the interrupts, right? After that, the timer interrupt will be delivered every 10 milliseconds, right? That makes sense? Okay, good. So, and which means that, you know, that's your way to essentially make sure that you implement something what is called fair scheduling, meaning that each process will have a chance to run for about the same amount of time on the CPU, right? So the timer will be, even if you have a process with an infinite loop or a bug, it will be periodically preempted and other processes will run in the system, right? So, okay, so cool. So wait, I asked the question. So when we are trying to enter the switch function, to switch from one process to another, what do you think has to happen inside the switch function?
You're gonna save all the data from the first process, stack, all the registers.
Right. And I will use this analogy of a box. So the box should contain all the state of the process, right? So if you were running this process P1 and it got preempted by the timer, right? And we want to switch to process 2 with this switch function, right? You have to pack all the state of this process P1 into this box. So if I ask you a question more specifically, what should be in that box? What is that state which you have to save? You started mentioning the state, but let's just take it a little easier, like a little slower, and understand what needs to be saved. Do you have an idea?
I think it's very similar to when we do the interrupt. Right? When we do the interrupt, we need to say like this many registers like step pointer, EIP, and
Actually, yeah, I agree with you. Like what you're saying is that we're gonna take inspiration from the interrupt pass. And in fact, we're gonna learn that almost everything is already saved. And there will be just a couple of registers which remain unsaved when we enter the switch function, right? Let me just go slightly backwards. So remember when I talked about this box, which I say represents a process, right? P1, for example. The process in the system is represented with this process data structure. I keep bringing it back, right? But intuitively, all the state, which is already like, which is in this data structure, like a page table directory, for example, points like to the page, like table data structure, right? So this pointer is around, right? So it's not going away. So you don't have to do anything with this pointer, right? So next time you will come to this process, can reuse this pointer and load it inside the CR3 register to switch to a new page table, right? For example, the name of a process, of course, doesn't disappear. The file descriptor table doesn't disappear, right? So none of it has to be saved, right? And in fact, if we like start looking at what is left unsaved, we should like kind of look at general registers, right? So we have 8 general registers, right? And you intuitively might say, okay, we have to save them all, right? Why not? In practice, however, most of them are already saved. Because remember that the kernel, which calls the switch function, follows the calling convention, which means that whoever calls the switch function already saved the caller saved registers. Remember, the registers are roughly split in half. And when you call a function, like if foo calls bar, some of these registers have to be saved by foo, and these are called caller saved, right? Which means that like bar will never even like bother to save those registers. It will just blindly override them. So if foo needs them after invocation of bar, it has to save them on a stack. Remember this idea, right? And the second part of those registers, they are called callee saved according to the calling convention. And callee saved registers are saved and restored by bar, right? Which means that when we call a switch function, switch internally has to save those callee saved registers, right? And there are not many of them, right? So literally there are just what? I think there are just four callee saved registers, right? So which means that when we enter the switch function, like EAX, for example, will be already pushed on a stack. If bar needs it, if foo needs EAX, it will save it on a stack before invoking the function, right? So, and we say, okay, look, we're gonna introduce a data structure, which we're gonna call a context. And this context data structure will have space for saving 4 callee saved registers, right? Plus instruction pointer. And we will understand why we need this instruction pointer later to kind of come back to where we were before the switch, right? But is this idea clear that everything else is roughly speaking saved? And I will illustrate it in a second again, but at a high level. Do we agree with this? Right? Okay.
It's possible to have different caller and calling saved rule, right?
Calling and caller saved what? Registers? Calling different calling convention?
Yeah.
Yes, correct. Then you will have to change the kernel to reflect the fact. So the kernel, when you talk about the context switch, you have to think about the calling convention which you are implementing. So yes, but again, that's partially why we spend time learning about the calling convention, just to be able to implement the context switch later on, right? Okay, but let me convince you one more time that everything is saved. So again, there's two boxes, like we're gonna go back to the timer interrupt pass again, but just at a lower level of details to understand how everything gets packed in a box for a process, right? So imagine you're running a process, right? So like some kind of a like code in user level, you have instruction pointer, like somewhere in the user address space, right? So this is instruction pointer value, you have ESP, you have EBP, you have your user level stack, everything according to the calling convention, you're running, you're super duper happy, everything is just fine, right? Inside the kernel, the process runs with some global descriptor table loaded in a register, some page table loaded in a CR3 register, right? It has a kernel stack because we're always ready to handle an interrupt. So we need to have this kernel stack, right? And a proc data structure. If it's your process proc data structure, will have a pointer to this kernel stack, will have a pointer to the page table, and we can talk about what happens to the GDT but a little later, right? Everyone agrees on that. So we're happy running. And suddenly, out of nowhere, timer interrupt arrives, right? So again, this is the very first step towards switching from one process to another. So we go through all this machinery, right? So we already know it. So vector 32, fetch entry 32 from the interrupt descriptor table. There will be a pointer to the vector 32 in the kernel code. We're gonna figure out the kernel stack from TSS, and the hardware will save these 5 registers on a stack, right? What's important towards our boxing or whatever this idea packaging the state is that those registers, those user registers, so for example, instruction pointer, which points to somewhere here where you were running, is already saved by the hardware, right? So we already know that it will be saved. Stack pointer, obviously, is also saved by the hardware, right? And these other 3 registers are saved by the hardware. So this is already in the box immediately when interrupt arrives, right? Then we descend towards the processing of the interrupt, vector 32, we push an error code and the number 32 on a stack, jump to all traps. All traps essentially, like this is on the entry of all traps, this is how our state looks like. So saved by the hardware, 5 registers, we saved nothing but like push these 2 numbers on a stack. All traps saves all the segment registers, pushing them on a stack, right? And uses this push all instruction, which saves all general registers. In the end, all these registers are saved on the stack. So what I'm saying here is that by the time we invoke the trap function, right, from the all trap, so by the time we invoke this call trap function, all the user registers will be saved on the kernel stack already. Agree with this? So we don't have to worry about them. They are already saved, right? So when we're gonna switch, it's fine. Those are saved, right? Then we start invoking like the C function trap. C function trap obviously goes through the interrupt processing path, reaches this yield function. The yield reaches the scat function. Scat reaches the switch function, right? Again, back to the box. Remember, like if we say that okay, our state is the stack, so why not to say that the kernel stack on which we started executing the interrupt will be kind of our box, right? Where we saved all the state, all the register state, right? So like again, like I will repeat what I said. This is saved by the hardware. This is saved by the all trap function, all traps function. So all the user registers are saved here. Then we started calling some other kernel functions, like some return addresses, some registers saved on the stack. If I ask you where are the caller saved registers? Where are they? Are they here on the picture? Anyone?
No.
No, why not? They're not in the picture, but they are somewhere hiding. Where? No, like before you call the switch function, imagine there was some value in EAX here. Let's say it's 55, right? You called the switch. Imagine switch, since EAX is a caller saved register. If you want to have this value here after the switch, before calling the switch, the compiler will generate the code which will push EAX on a stack, right? Saving it, right? And that's one example of a caller saved register, right? So specifically, they will be saved somewhere here on the stack, right? Agree?
Yeah.
And then we suddenly call switch function, right? But did I convince you that we saved almost everything? We just, again, remember, there will be this context data structure, which will have this 4 registers, 4 callee saved registers, which are still unsaved. But everything else is saved. Do you agree with this? On the stack, right? So this is the stack. Okay, so switch takes 2 arguments. It has a pointer. It has 2 pointers. It has a pointer to, okay, essentially, roughly speaking, it has a pointer to the new context, meaning that the new set of those user registers, which is going to load into the real hardware registers. And this is the process we are switching to. So this is the new process. And it has a pointer which describes how to save the current context, like current, old, unsaved callee saved registers, right? So you need 2 locations. You need to save the old context and load the new one, right? And roughly speaking, those are the arguments. And we will understand in a second how they are implemented. But at a high level, this idea is clear. Only 2 arguments, right? So 1 and 2. Agree? I will explain in a second, but just there will be 2 pointers, right? Okay, so our goal at this point, when we enter the switch function, is to first save the unsaved registers into the context, right? And then load these new registers from the context which is provided to us, right? And that's essentially, that's the switch function. So nothing else needs to happen. So if you really save those registers, the old registers, load the new registers, and then somehow change the instruction pointer to the new process, you're golden, right? So it's very, very simple. Literally, save 4 registers, do something with the instruction pointer, and load the new 4 registers, right? That's the whole switch.
This stack is in user space or kernel space?
Good question. So who knows it?
I guess both.
It's in kernel space, but you look bored. So we need to pick someone from the back who didn't follow. Hold on. Do you remember which stack is that? So remember how everything started. When we started switching the interrupt paths, right? The hardware switches to this new kernel stack. We cannot stay on the user level stack because it might be invalid. We don't trust the value of the user stack pointer, right? That's why we have for each process running right now, for each process in the system, we'll have a kernel stack. And this is where the hardware starts saving this five registers and switching to it, right? And this stack starts growing. So essentially, initially it's only 5 arguments. Then we add 2 more by pushing these 2 values. Then all traps add more registers here, but that's the same stack. So it's the same stack which I'm drawing here. This is the kernel stack of a process, right? Do you understand? Does it make sense? It probably should, like, it's a good question because
So
every,
is kernel stack in the kernel space?
how many kernel stacks do we have in a kernel space? It's a great exam question. So who can tell me? Who knows the answer? That's a sound idea, but no. And I can, like, after today, it will become clear why it's not done. Although again, that's a great. So what your classmate is saying is that, okay, let's come back to the question which I asked. So how many kernel stacks do we have in a system? It's an exam-worthy question. One per process. That's almost the full points minus 5 whatever points. And to gain this last 5 points, so who can improve the answer? Okay, first of all, you're right. One per process. One per process. Plus what?
Do we have kernel stack initializing?
Correct. So we also have a main stack on which we booted, right? And it's not clear up until now. So right now we've seen only one, but it's one per CPU. One per CPU. So on each physical CPU, we kind of enter a similar main function. On the first CPU, it's called main. On the second CPU, it's called MP, multiprocessor main. And each of them will have its own kernel stack. And this is done on this stack, the scheduler will be running, meaning that if there are no processes in the system, you're still running correctly, right? And so that's the answer. So essentially, if you have like 4 CPUs, you will have 4 kernel stacks, 4 main functions. And if you have 10 processes, then it will be 4 plus 10, 14 stacks. And I will come back to this observation whether we really need a physical page for a different process. If you carefully follow how we created the process in the exec function, you saw that we allocated a physical page. So each process will literally have a new page which will hold its kernel stack. But after today's lecture, it will become clear why it's done this way. It doesn't always have to be this way, but it's done this way in x86, right? Okay, so good. We got to this. You were asking, I forget what was the line. You were asking
How many
kernels? Okay, again, when I was a student, I was also surprised because my task back then was to build an operating system which can run as many small processes as possible, like kind of Apache on steroids, forks on every incoming request. And I was saving pages like crazy. And I was very surprised that I still, even in a system like back then, it was FreeBSD was my system of choice with which I was working, that I really have to waste a page on a kernel stack. It was a surprise, but for you, it shouldn't be a surprise if anyone asks you to say, look, I really need a kernel stack because I have to process interrupts. I don't trust the user value and stuff like that, right? I mean, again, in real world, you can design stuff differently, but that's a subject for the advanced operating system class. Okay, we get back to switch, right? So do we agree that we packed almost everything on a stack? Inside the switch function, we're going to do the following. We literally will save those 4 unsaved registers in assembly because we don't trust the C to generate the code correctly, right? So we say this function really has to be in assembly. And we have these 2 arguments, right? So, and really this layout matches the layout of this context data structure. And it doesn't have to be this way always, but x86 chooses to allocate this context data structure on a stack itself, right? So really it can be a different data structure. And then instead of those pushes, you will use like kind of a move, which takes an address of the data structure and a register, right? It's totally fine. But x86 says, okay, I will allocate this context data structure on the top of my current stack, which means that, okay, this is the stack, right? So, and the context will be sitting over here, right? Why not? I mean, As long as you have stack space, that's totally fine. And so to save the registers, they will just simply pushing on a stack. And the order of these pushes matches the layout. So EBP, then EBX, and so on, ESI, right? So layout of this data structure. Is it clear, this trick?
Where is the EIP?
Where is the EIP? Gonna talk to it. Okay, where is the EIP? When we call the switch, it's a return address, so it got pushed on the stack already, right? By the caller.
Oh,
When you do call switch, this instruction call pushes the EIP on a stack, right? So it's already on a stack. And since we handcrafted this function, we don't maintain the stack frame pointer here. Just forget about it. We don't need it.
So how does the context structure get a value? Yeah, it's on the stack by the caller. But what's the moment the context has this value?
Just bear with me for a sec, and we'll see it. So okay, so a trick which I was just describing is that in x86, the context is saved on the top of a stack always. Again, no need to be this way always, but x86 does it. Okay, we saved all the registers, right? At this point, we say, look, if we know that, like we save them, we're ready to switch to the new context, right? So not surprisingly, and remember what we have here is the following. If we have this trick that the two arguments, or one of the arguments which got passed to x86 is a pointer to the new context, right? As we said, it happens to be the top of some stack in x86. That's okay, we don't care. We only care that we have a pointer to the context, and this pointer to the context was passed as one of the arguments, right? And what we're gonna do is that, again, if we learn this trick that we said, okay, we saved our context on the stack. That's our context data structure. In order to come back to it later, we're gonna save it, right? So our context is currently on the top of our stack. So our ESP register points to our context, right? And the second argument which is passed is the memory address where this pointer has to be saved. So essentially, we want to establish this line, this error, right? It's natural. You say, look, I have a context of the currently running process. I have a process data structure. So naturally, the process data structure will have a field which will be a pointer to the context of this thread, of this process, right? And the address of this field is passed as an argument into the switch function, right? So more specifically, this is it. So it's passed on a stack. So we use the following the calling convention. So it's ESP +4, and this is the pointer to a pointer field, right? So it's like, let me draw it again for you. This is the proc data structure, proc. It has a context. Let me erase a little, just to make sure that I can draw a pointer. It has a pointer field, so it will be a star, agree? Context. A pointer field. And what we're passing here is a pointer, this one, which essentially points to this field. So it's a pointer to a pointer. Agree? So what we're going to do is we update this pointer here to save, to make sure that this context points to the top of our current stack. Does this idea make sense? It's not very hard. So, you know, you pass the pointer to a pointer, you load it, you save it in the AX register, and now you're simply saying, okay, I will save the current value of ESP, my current stack, where the context is located, into the value pointed by the EX register, right? That's how we save the old context, right? Agree? Everyone is clear? This is, I mean, again, nothing really special happens here, but I just want to make sure that we all understand. Yes, no? I will show you again this diagram. So erase everything. So proc data structure has a context field, which a pointer to this context field is passed inside the switch function as an argument. the current context which we saved, right? This 4 registers is in the top of our stack. So what we're literally doing, we're saving this value of the ESP into this field, right? Agree? And we remember the state of the current process. So how do we switch to the new one? As I said, the second argument to the switch function is a pointer to the context of the new process, P2, right? Again, we know that the context is allocated on the top of some stack, but it doesn't have to be this way. But really, it's not hard. So if you know that you have this context, right, passed to you as an argument, it's again ESP plus 8. We save it in the EDX register, right? Those are actually wholly saved registers, so we are free to use them. We can override them without pushing anything on the stack, right? We're gonna simply load this EDX into the ESP register, right? So we're gonna say, okay, if this was passed to us as an argument, we're gonna establish this pointer. Hardware ESP register will be pointing to the current context, to the context of the new process, pardon. Is that clear? Right? And after we did it, okay, what do? We pop the registers, obviously, because we say we're gonna restore them, right? So that's not super hard. Again, we just pop the registers, right? Meaning that we switch to the new box. Again, all the other stuff is packed on that box, right? So it's somewhere, since we said, okay, the context is top of some kind of a stack. So everything is packed here on this stack. Only these 4 registers are not like we have to restore them, but they're also packed inside the context, right? And so that's what we're doing here. We restore those registers, right? Agree? So the only one bit of state which is kind of still in flight is the instruction pointer. Because remember, we were executing in the old process, P1. We want to start executing in the new process, P2. So at some point we say we want to reload EAP with something, right? How are we gonna do this? Shy hands. Exactly. So remember, x86 doesn't really have an instruction which allows you to load inside the instruction pointer. So one way to load something is you can jump to an instruction pointer, you can call into instruction pointer, or you can return. And this return instruction specifically just does this. It switches to the instruction pointer of the new process, right? Okay, incidentally, this instruction pointer sits right here at the very top of the context, right? So, or bottom of the context data structure, but very top of your stack, because that's where this trick becomes convenient, when you push the context at the very top of the stack. So you already like pop these values, right? Stack points to this location. So if you're gonna do a return, it will return to this address, right? And this is the address which was used previously by this other process to which we are returning, right? So this return instruction finishes the context switch, right? So if we call this switch function in one process, right? Let me come back to this invocation of switch. So let me erase everything. I'm sorry. We were running inside, we were running inside P1. We called inside the switch. We're not going to return here, right, immediately. We're going to return here later on, after many timer interrupts potentially, right? Eventually we'll come back here. But instead, the process P2 to which we're switching at some point in the past called this switch function as well, right? And we're going to return exactly here, right? Inside the P2, right? We are switching from P1 to P2. Does this make sense? Okay, so that's the context switch. So I will ask you a question. So we save the state, everything is fine. We kind of understand that the switch doesn't return to where we started, but it returns somewhere else to another process. And if I ask you a question, where do you think this switch returns? Just it requires kind of like cross-cutting reasoning. So you started from the timer interrupt, you went through the kernel, you did the yield, you did SCAD, you did switch, and you're jumping to kind of a different process. But where? What is this process, or what is it? Where are we returning, or where are we switching to? No, correct. Roughly speaking, to the like if that other process at some point in the past invoked call switch, right? We're gonna return to this instruction at address A here, right? But what is this process? Which one is that? Almost. It's a kernel scheduler.
Yeah.
Right? Because logically, what we want to do is that we want to pick a next process to run. Again, there are multiple ways to design it, but never on this timer interrupt path we yet looked at the next process to run. And the way x86 does it, it really switches into the scheduler. The scheduler will be an infinite loop, which will pick the next process from the process array to run. We'll pick one, and we'll switch again to this process, right? And this is how it works in x86. So you switch from process one to a scheduler, which picks the next process, switches to the next process, right? So it's kind of like a little bit to like extra overhead because you do two switches, right? But it's okay. It's okay. Let's take a look at how we actually arrive to the scheduler, right? So we never yet talked about it, right? But I'm back to my main function. It's the beauty of it is that you're gonna know everything, right? So, but look, you're at the very end. Looks like you're almost done with this class, right? So last function in main. So what can go wrong here? So at the very end of main, we enter this function MP main, right? MP main itself just prints something that CPU is starting, does a little bit of loads the interrupt descriptor table, and enters the scheduler function on each CPU. So, but we're still on the CPU number one. So we started from main. And what is this scheduler? The scheduler is literally an infinite loop. It will never exit. It runs on that kernel stack, which we mentioned. There is a kernel stack per CPU on which we booted into main, right? And what it does here is says, okay, I have a process table. I have another loop inside, which is going to loop through the process table from the beginning to the end. And when it reaches the end here, it will start over from the beginning. So it never exits. It's all just going through all the processes in the system forever. It takes a look at the entry at the table. If it's not runnable, it picks the next one. So essentially continues, right, to the next iteration of a loop. If, however, this process is runnable, it says, okay, it will be my current process. It will switch the address space, so essentially switch the page tables. It will set the state of this process to running, and it will switch into it with the switch function. It's exactly the same, just the two arguments will be these. This is the pointer where the context of the scheduler will be saved, and we're using a pointer to a pointer, right? So we're passing this ampersand. And this is the context of a process we want to run, right? And remember, when I talked earlier today, when we did this alloc proc, I kind of skipped it, but when we create a new process, we actually initialize this context correctly in order for switch to work, because we have to set up the context in such a manner that we pretend that it was earlier preempted by the timer interrupt or some other kind of interrupt. So it entered the kernel. So there will be all the same data structures on the stack, like as if they were saved by the all traps and so on, right? But it never happens for the new process, right? So the very first time it runs, so the very first init process which we created, we will initialize this context correctly as well. And the scheduler switches to this, right? And the process starts running, right? And so when we're switching from the process to back to the scheduler, not surprisingly, right, you arrive on which line? Who can tell me the line number? So we were switching from a process back into the scheduler. Which line will be executing after the switch?
2479.
Correct, to 479, because it's the line right after the switch, right? And so it switches back to the kernel address space, sets the process to 0, saying that, okay, I don't have a current process, and continues with this loop to essentially pick up the next process. And it's the scheduling policy is very primitive. It's called round robin. So essentially, it will literally go through the array one by one, and like go and every process will have a chance to run. It's not very fair, because if you say the process is somehow not runnable, maybe it's waiting in a sleep function for some number of ticks, right? It will skip its chance to run. So overall, processes which will be sleeping will spend less time on a CPU. So modern operating systems account for that, but we don't care. It's good enough. So if you're building your operating system, like you go, again, I'm saying like something like a Fitbit style wristwatch, which shows the number of steps you walk and stuff like that. That's okay-ish. That's a good enough scheduler. So again, if you suddenly want to do a startup tomorrow, which has a wearable device, just go for it. So this code should work, right? Okay, cool. Any questions about it? So this switches from the kernel to the user. So it's a switch of a page table. This switches back to the kernel page table on which we booted, because there is a chance that the process will be deallocated. Because it's like, remember, you've seen it before, that there is this check that if the process is killed, this is when they start deallocating the page table. So in no part of the system, this page table of this process has to be used. That's why we are switching back to this kernel page table here. So, but the switch kernel virtual memory essentially reloads the CR3. Another question?
So the number of schedulers should be, the scheduler is always running, right?
Right.
So the number of schedulers should be the number of CPU.
Correct. So on each physical CPU, we're gonna initialize the scheduler. And next time I will explain briefly how multiple CPUs are bootstrapped in x86, because we're gonna be talking about synchronization and why you need those acquire and release locks and stuff like that. So there will be a scheduler per CPU.
So the first, I'm still not so clear about the stack switch process.
Stack switch, what do you mean?
You said save the old stack and switch to the new stack. Yeah.
Right. So you mean inside the switch function, right? Something like this. Is that what you're asking?
Yeah. The code. How about kind of code?
Yeah, we can take a look. So let me come back. So that's a good question. So the two arguments which are passed to the switch function are those two. So one is a pointer to the field. It's a pointer to a pointer, where we're gonna save the context of the old process or the current process, right? So we will establish this pointer, right? So the argument is actually memory location of this, like the address adder of these 4 bytes, which contain the pointer value, right? The second argument is the pointer to the new context, right? And in x86, by design, that's how they decided to do it, but you can do it differently. The context is always at the top of some stack, which means that like you can return to this address, right? And just continue returning on this stack, and you will be running in a new process. Or in x86, if you're switching from a process to a scheduler, in my slides, I show here that the kernel stack, it's a kernel stack of a boot process. So you're switching from a current process to a scheduler, right? You have these 2 arguments, right? So, and the code is reasonably simple. So it literally just what it does is just says, okay, these are 2 arguments. I save one of them inside the EAX register, another inside the EDX register, right? And here, since I'm saving the context of the current process, and the context is top of my stack, it's pointed by the ESP register. So I simply save it into the memory location pointed by EAX, right? And EAX was passed as a pointer to a pointer, these 2 stars here, right? Agree? And then since you want to switch to a new context, you say the new context is passed to me on a stack. I loaded it into the EDX register. I simply load the EDX register in the ESP pointer. And at this point, my ESP pointer, let me erase everything on this, will be pointing to this new context. And I can start restoring the call is saved registers from the context, right? Agree? And I keep saying that the context doesn't always have to be the top of the stack. You can put it in literally, you can put those registers in the process data structure. It's okay, because it doesn't matter. So maybe the only trick you will have to do is that you, at some point, you have to put the instruction pointer on the top of the stack so you can return to it. You don't even have to return to it. You can jump to it if you like. So, right, there are multiple ways to build it, but x86 builds it this way, right? Any questions about the context switch? Good. So what did we learn here? So we learned that, okay, every CPU ends up running a scheduler. So the scheduler runs on this kernel stack. At some point, it switches from the scheduler to the very first process, right? And then this very first process switches back to the scheduler, and so on, right? And I will maybe we can actually stop kind of here. So because that's all what we need to understand, like in terms of context switch. Good. So then next time I will talk about how we initialize multiple CPUs and what does it mean to, why do we need synchronization? So we'll see you then Thursday.
Just to figure out the problem unless you.
No, I simply didn't have time. Realistically, let's do it on after the 20th, because
After.
April 20th. So I don't think I will have time to spend on it.
Okay. Probably I will have some more questions in off the hour.
Yeah, okay.
Thank you.
What's up? Not booting again?
No, I'm still.
Okay. So do you have time? You can come over. I can fix it for you probably.
Yeah, but
But go ahead.
the thing is,
Wow, that's cool. Learn how to split it.
the thing is, you mentioned on the PRs to use that M thing, and I'm not entirely sure. There's a shortcut I know to like back out of it, but there's no reason I couldn't.
No,
I
but
couldn't
you
do it.
like what it tells you here. Look, it's a security mechanism which says I do not allow auto loading. So you need to.
Yeah, you add that to the.
Yeah. So did you add?
Yeah, I did.
You did.
Yeah.
So now it allows. It's still complaining.
Yeah.
No, it is complaining. Like
That's,
when you see this line, it means that it's not working yet.
yeah, it's fine.
Yeah.
I did add it.
Maybe you add it for like. Okay, let's just for you, like maybe you edit for a different homework, like let's just auto load from anywhere. It's not very secure, but you will probably will be fine. So let's quit, and I will do win. Sorry, I'll just win. Yes, I can't use anything else.
GDB.
So you don't even have GDB in your system somehow. You know, like I will edit.
Oh, I can't see it.
Maybe you used for
Right here. It's in the same folder. Okay.
yeah, but you probably can do it differently, but I will put it inside your like control V. Right click.
Yeah.
Oh, okay. What's the right for you?
I don't
Yeah, right Q. What? Right is not working. Read only. So you file auto loading has been declined by your auto load. Auto load.
I think you. So you, wait, this is different GDB, so that's not this one. You really need a new phone, so.
It needs to be in the file.
But why is this already exist deleted? Add this. You'll never see this line again. Controls. It's not control C.
You have to left, right click. It's Control shift.
You paused it here. Oh, actually, I should probably stop.